Okay, hello people. This is an update to number 138 on homework set for chapter 5. As many of you witnessed in the recitation, my brain exploded. So, here is the promised review video for that problem. Okay, so the problem is basically setting us up with the knowledge that C2H2 decomposes into C6H6. It tells us that it starts out at 7.8 kilopascals of pressure in the initial container that the C2H2 is held at. So initially, the only thing that's in the container is C2H2. And over time, this reacts and this stuff decomposes into C6H6, and it forms instead a pressure of 3.9 kilopascal. Okay, so there's a drop in pressure, and the question is asking what percent of C2H2 reacted. Okay, so that's what we want to try to solve for. Let's go through a little bit about what we know about the problem. So C2H2 reacting to form C6H6 is it's not a balanced equation. We have to balance this, and it turns out that it's really easy to balance. So 3 moles of C2H2 will react to form 1 mole of C6H6. Okay, so in the initial state, we also know that the total pressure is equal to the partial pressure of C2H2 because that's the only thing that's present in the system, and this is equal to 7.8 kilopascals. And then the final state is a mixture of C2H2 and C6H6. So we have to add these partial pressures together. And this total pressure equals then 3.9 kilopascals. Okay? So in the first case, there's no C6H6, and in the second case, there's a mixture of these two gases. Okay, from the stoichiometry of the problem, we know that 1 mole of C6H6, that's a bad 6, sorry. 1 mole of C6H6 is produced by 3 moles of C2H2. Okay, we know that we know this from the stoichiometry, and furthermore, we know that this is reacted C2H2. Okay, which is important because that's what we're trying to get to. Let's think about this a little bit more graphically. If we have 3 moles of C2H2 and we react them together, we form 1 mole of C6H6. Okay, so in this case, our number of moles at the starting position is equal to 3 moles. And in the final case, our number of moles is equal to 1 mole. Okay. Now the important thing here is that in the equation PV equals nRT, the N here does not care if it's C2H2 or C6H6. Okay. This doesn't care what the N identity is. It just cares about the total number of molecules or moles. Okay, so it only cares about the total number of moles. It doesn't care about what they are. Okay, and it also shows that pressure is proportional to the number of moles. So if we have a total mole drop, so the total number of moles drop by 2 overall. Okay. And this is just 3 moles in the beginning minus 1 mole at the end is equal to a 2 mole drop. So there's a 2 mole difference between the two. And this occurs with every 3 moles of C2H2 that reacts. Okay, so for every 3 moles of C2H2, we drop the total number of moles by a factor of 2. And because the pressure is proportional to the number of moles, we can say that the pressure is going to drop by 2 kilopascals. Remember, pressure is proportional to the number of moles, so it drops by 2 kilopascals for every 3 kilopascals of C2H2 reacted. It might be weird to think of it in this way, but we can think of a gas as having a pressure or a gas as having a number of moles, simply because this is true. The pressure is proportional to the number of moles. So we can write it this way. And the nice thing about this is that this provides us a conversion factor. So we can say that there's a 2 kilopascal pressure drop for every 3 kilopascal of C2H2 reacted. Okay, so this is starting to look a little bit like a conversion factor. What do we know from the problem? Well, we know the pressure drop, right? We know the delta P of the problem. We know that this is the pressure of the final state minus the pressure of the initial state, okay? And we can actually determine the amount of reacted C2H2 by multiplying this change in pressure by our conversion factor above. So we multiply this by, well, it's the inverse of this. So it's 3 kilopascals of C2H2 reacted divided by 2 kilopascals of pressure drop. Okay, so we're taking our pressure drop from the reaction, and we're multiplying it by the amount of C2H2 reacted per the amount of pressure drop. Okay, so we can go ahead and calculate delta P. We're given everything we need for this. So that's the initial state. Oops, I have this backwards. Sorry. No, that's right. Final minus P initial. Oh, whoops. Okay, so actually, if I want to know the pressure drop, not the pressure increase, I mix this around. Okay, so instead of final minus initial, it's initial minus final, because I want to know how much it's actually dropped over that range. Okay, so in this case, it would be initial pressure, which is 7.8 kilopascals. That's the initial pressure, minus the final pressure, which is 3.9 kilopascals. And the difference between these two is 3.9 kilopascals. Okay, so now we have the pressure drop in the reaction. And we can just plug this in here into our conversion factor, and we can get the amount of C2H2 that has reacted. So reacted C2H2 is equal to 3.9 kilopascals multiplied by 3 kilopascals over 2 kilopascals. So that's C2H2 reacted divided by pressure drop. Okay, so kilopascals cancels out here, and we end up with, let's see here, 5.85 kilopascals of reacted C2H2. Okay, so 5.85 kilopascals of the initial 7.8 kilopascals of C2H2 has reacted, but we're asked to find the percentage of reacted. So percent reacted is simply equal to 5.85 kilopascal divided by the initial amount, which is 7.8 kilopascal, multiplied by 100%. And this gives us 75% at 2 significant figures. Okay, so the amount of C2H2 reacted is 75%. Okay, the reason that this is a bit tricky is that you have to recognize that you can build a conversion factor from this concept here, where you're taking 3 moles and you're scrunching it down into 1 mole. But you have to realize that the total number of moles, it decreases by 2. Okay, so there's a total decrease in 2 overall moles for every 3 moles of C2H2 that's reacted. And once you see that, and you see that the pressure is proportional to the number of moles, you can come up with this conversion factor here, and the rest is pretty trivial. Okay, that's all I have for you. I hope you guys have a great weekend. Bye.